Welcome students of Thakur Vidya Mandir High School and Junior College. Students, we are back with the part 2 of chapter 1 rotational dynamics. In part 1 we have studied uniform circular motion, whereas in part 2 we are going to study the continuation, that is vertical circular motion. Let us take down the first example, that is conical pendulum. Conical pendulum is a tiny mass connected to an inextensible string suspended to a rigid support. Conical pendulum is a simple pendulum which is given such a motion that bob describes a horizontal circle and the string describes a cone. This is very clearly seen in the diagram given here. When I talk about the diagram, slant height is represented by small l. The two forces which are acting on the bob are represented by t cos theta and t sin theta. The weight of the bob is given by the formula W equals mg. Consider the bob of a mass m moving along a horizontal circle of the radius r with a velocity v. When we see on the right hand side of the diagram, the t sin theta is nothing but the centripetal force which is acting on the bob, describing a horizontal circle. Therefore, it is given by the formula mr omega square. The tension in the string t cos theta is given by mg, which is equal to the weight of the bob. The radius of the circular motion is written by small r is equal to capital L. Let us talk about the time period of the revolution of a bob, and it is given by the formula omega, where omega is equal to 2 pi divided by t. If I talk about the periodic time of a conical pendulum, it is a time period which takes to swipe one circle of a circumference 2 pi r, and the speed with which it is moving is represented by a small v. So the final formula of the time period of revolution of bob is given as omega is equal to square root of L multiplied by cos theta divided by gravitational force, that is small g. Let us talk about the frequency of the revolution. The frequency of the revolution is given by a letter small n. Small n represents the formula which is reciprocal of the time period. Therefore, the frequency of revolution is n equals 1 upon t. The second part of today's topic is vertical circular motion. Vertical circular motion is of two types which are commonly observed in practice. A controlled vertical circular motion is either kept constant or not totally controlled by the gravity. Examples are giant wheel or similar games. The second vertical circular motion is controlled only by gravity. In this case, we initially apply the necessary energy at the lowest point. There is an interconversion of kinetic energy and gravitational potential energy, where you could see the reversible arrow changing from kinetic energy to potential energy. Let's move to the diagram of vertical circular motion, where we have given the example of a giant wheel. You could see the four positions on the circle, that is the uppermost position at A, the bottom position at point B, and the two horizontal positions denoted by the letters capital C and T. Let us talk about the tensions that are present on the uppermost position and the lowermost position, as well as the horizontal positions of the giant wheel. When I talk about the uppermost position, the speed at the uppermost point is given by VA. VA is given by the formula where the tension A is an addition of mg represented by mv square by r. This is the centripetal force which balances an addition of weight of the body plus the tension which is present at the topmost position A. Let us move on to the lowermost position, that is B. If I talk about the speed at the lowermost position VB, it is given by the formula tension B minus mg, that is the weight of the body, which is equivalent to centripetal force which is acting on the body. Therefore, it is given by a formula Tb minus mg is equal to mv square by r. Let us move on to the position where the string is horizontal at the points C and D. Therefore, we could say that the tension is a subtraction of Tc minus Ta. That is, the horizontal point at point C is subtracted by the tension present at the point A, that is the uppermost position, which is equivalent to the point D again on the horizontal part of the circle, where the tension D is again a subtraction with the tension A which is present, which is equal to thrice mg. So if I talk about the velocities at the horizontal positions at the point C and D, it is given by the formula Vc is equal to Vd, which are at the equilibrium positions represented by square root of 3rg. These are the classical formulas which have been derived by considering the tensions present at the positions, that is the topmost position, the bottom position and the horizontal positions. Thus, it gives us a clear picture about the vertical circular motion. I will give you one more example of a vehicle at the top of a convex bridge. Students, we move towards the bridge when we are going to the native place. There you could see a train or a truck or a vehicle moving on a bridge which is convex in nature. So let us talk about the vertical circular motion which is acting on such a vehicle. When you see the diagram, you could see the bridge in a convex form and the vehicle which is moving on the bridge. The normal n is acting perpendicular to the line where the weight mg is acting vertically downwards. R is represented by the radius of the convex surface of the bridge. Let me discuss about how you deal with a vehicle when it is moving on a convex bridge. The forces which are acting on a vehicle are: first, that is the weight mg acting vertically downwards. Second, the normal reaction force which is acting vertically upwards along the vertical line. If I have to calculate the speed at the uppermost position, I will calculate it with the formula mg minus n, which is equal to the mass multiplied by the centripetal force, that is mv square r divided by r. As the speed keeps on increasing, the capital N normal goes on decreasing. Therefore, the final value for capital N turns out to be 0, and the V max at this particular point for the vehicle is represented by root Rg. Another example of vertical circular motion is evident by a motorcyclist who is riding in the sphere of death in a circus. The dynamics which is being followed in this motion is same as the vertical circular motion. The tension that is present in the sphere of death is replaced by the normal reaction. Thus, the motorcyclist makes all the possible horizontal circles which are as equivalent to the one which is made by the giant wheel. Let us talk about the speed of the motorcyclist who is moving around in the sphere of the death. The linear speed is more for the larger circles, whereas I compare to the angular speed with which the motorcyclist will ride is more for the smaller circles. So these are the two conditions which specifies the speed of the motorcyclist in the sphere of the death. So students, we complete all the examples that were related to the vertical circular motion in this part 2 of rotational dynamics. Let us move on to the assignment questions which are mentioned out here. First, define conical pendulum and obtain out its expression. Try to make a neat label diagram of vertical circular motion. Thirdly, you can derive an expression showing the tensions at different positions in vertical circular motion. Finally, the motion of a vehicle on the top of a convex overbridge. That is the last diagram which I have shown you. If any doubts, please refer on to the e-textbook links which are mentioned down over here. I hope all the doubts are clear. Thank you.